Welcome to the Fundamentals of Modern Protective Relaying. The goal of this course is to provide you with an understanding of modern protective relaying and its application within common power systems. This course is comprised of 5 sections: power systems, distribution, transmission, motors, and generators. Within the first portion of the power systems section, you will become familiar with the configuration of common power systems and the role of each major power system component. This is followed by an in-depth examination of the function, equipment, and requirements of protective relaying equipment. You will then be introduced to protective relaying concepts such as zones of protection and primary and backup relaying before being taken through a review of AC theory as it applies to protective relaying. The distribution section focuses on the protective elements, operating characteristics, and coordination used within distribution protection. You will be shown how these elements and concepts are formed into a protective solution for feeder, bus, and transformer applications. The transmission line section will introduce the terminology used, followed by a detailed examination of the different protective schemes used for transmission lines. The protection of rotating equipment has been divided into 2 categories: motor and generator. Within the motor protection section, you will first be introduced to motor theory and motor thermal modeling. These topics will be followed by additional protective elements essential for a complete motor protective solution. Within the generator section, you will be introduced to some of the more common generator configurations, including their advantages and limitations, before proceeding on to the associated protective elements and their requirements. Once you've completed this course, you will have obtained a thorough understanding of the fundamentals of modern protective relaying. Introduction to the power system. Modern electrical power systems are remarkably dependable, delivering energy 24 hours a day, 365 days a year, without interruption. Protective relays have an important part in assuring this continuous service. The protective relay is always ready to react instantly to protect the system from damage and to minimize any service interruption. To better understand how protective relays fit into the modern power system, we will first review the makeup of the system. A power system is designed to generate electric power of sufficient quantity to meet present needs and estimated future demands of the users in some particular area, to transmit the power to the area where it will be used, and then to distribute the power within the area. For normal operation, these are the minimum requirements. Let's take a closer look at the key components of a power system. The potential costs due to equipment damage, interruption of power, and associated safety issues give a high priority to protection. For example, if a small section of aging insulation in a large distribution transformer fails, high levels of fault current will flow. If the fault isn't isolated quickly, the fault current will cause the conductors to heat. As the temperature of the conductor rises, the damage will spread to the surrounding insulation, causing it to fail, and the fault current will increase even further. As the level of fault current increases, the temperature will rise to a level that will melt the conductors and burn the steel laminations, resulting in catastrophic damage to this inadequately protected transformer. There are many causes of power system faults: lightning, wind, and ice and snow, just to mention a few. The protective system must be able to sense the fault and take appropriate action within a time frame necessary to minimize damage. Faults may be intermittent or permanent in nature. Lightning striking the transmission line, or a strong wind causing 2 phases of the transmission line to touch and form an arc are common causes of an intermittent fault to an overhead transmission line. The resulting arc ionizes the air and turns it into a conductor. The arc is then maintained by the power in the line. In both cases, the protection system responds by removing power from the line for a period of time long enough to allow the ionized air to dissipate, and then reapplies power to restore service. Physical damage to a power system component, such as the transmission line or towers, are 2 examples of permanent faults. The protection system must be able to quickly sense and isolate the faulty components to minimize damage. There are many sources of electrical power: gas, nuclear, hydroelectric, and alternative. The electrical power that is generated by these sources must equal the power that is consumed. Let's take a look at a simple system consisting of a generator, steam turbine, prime mover and control system, and a residential load. As stated, the generated power must equal the demand, which is constantly changing. As the load increases, the generators would tend to slow down, resulting in a reduction of output voltage and frequency. The generator's control system will sense this and input more mechanical energy to match the increased load. If the demand decreases, the generator will speed up. The control system senses this and then takes appropriate action to reduce the mechanical energy input into the system. Once generated, the voltage is fed to step-up transformers for transmission to reduce the I²R losses, and then at the substation it is stepped down for distribution. Given that the power loss during transmission is equal to the current squared flowing through the transmission line times the resistance of the transmission line, the step-up transformer increases the voltage level, thereby reducing the current, resulting in an overall reduction of power loss during transmission. The Institute of Electrical and Electronics Engineers, sometimes referred to as the IEEE, have divided voltage systems into low, medium, high voltage, and extra high classes. Low voltage systems are below 1000 volts. Medium voltage systems are between 1001 and 100,000 volts. High voltage systems are between 100,000 and 230,000 volts. And extra high voltage systems are considered to be any system above 230,000 volts. The voltage levels may vary in different parts of the world, but the names of the classes for the most part remain consistent. The three-phase power travels from the generating station over high power lines to substations. Different voltages are required for residential, commercial, and industrial customers. And so, at substations, breakers and transformers route and step down the voltage to a suitable level for distribution. Let's take a look at a typical distribution system for a residential customer. Let's recap. The generated power is transmitted via high-power transmission lines to a substation, where it is stepped down and routed to residential users. From the substation, the residential power lines take the power above or below ground to a transformer, which steps the single-phase voltage down to a suitable level for home use. From the transformer, the power then enters the home through a metering device and is then routed to a load center. From the load center, power is routed to different areas of the home. The distribution system for a typical industrial or commercial user shares some similarities to that of the residential customer, with the major exception that the power being delivered is usually three-phase. From the substation, the industrial or commercial power lines take the power above or below ground to a large transformer, which steps the three-phase voltage down to a suitable level for the plant or building. For larger commercial or industrial users, this voltage may be in the medium voltage range. In this case, there will be an additional substation on site. The power would then be routed from the transformer or transformers via medium or low voltage switchgear to different areas of the plant or building for further distribution via switchboards and panel boards. The power system can be thought of as a chain, the links of which are the generators, the power transformers, the switchgear, the transmission lines, the distribution circuits, and the loads. The arrangement of these links are as shown. The failure of any link destroys the capacity of the chain to do the work for which it was intended. One way in which the continuity of the chain can be preserved is to provide alternate links. For example, the transmission lines, being exposed to the natural elements, are much more vulnerable to short-circuit faults than the power transformers and switchgear. Hence, alternate transmission lines may be economically justified, whereas alternates for the power transformers and switchgear would not. The network of power systems now blanketing North America are often interconnected at various points to accomplish this. Since each link in the chain involves a large investment in equipment, alternates are frequently prohibitively expensive. To ensure both maximum return on the investment and to provide reliable service to satisfy customers, the whole power system should be kept in operation. This is accomplished in two ways. The first is by the specification of the design and the maintenance of each component of the power system to prevent a failure which would affect the component's usefulness in the power system. The economic considerations of design and maintenance procedures will allow this to proceed only so far. The second procedure which is followed is to control and minimize the effects of any failures that do occur. This is where the protective relay fits into the power system. The protective relay is the device which operates to disconnect a faulty part of the power system, thereby protecting that part and the remainder of the system from damage. Protective relays are placed on the system to reduce the number of alternate links to a minimum. They do so by avoiding equipment damage or by limiting it to the single component that may be in trouble. The relays quickly locate the fault and trip circuit breakers, which will interrupt the flow of current into the defective component, thereby isolating it. Two benefits of this quick isolation are, first, it minimizes or prevents damage to the faulted component, thus reducing the time and expense of repairs, and permits quicker restoration into service. The second benefit is that the quick response minimizes the seriousness and duration of the fault's interference with normal operation of the unfaulted parts of the system, allowing them to continue to supply their normal power. In many cases, the unfaulted parts of the power system can supply the additional power to replace what was normally supplied through the faulted component. The protective relay uses current and voltage instrument transformers to acquire information about the system, such that a fault can be located. The type and location of the instrument transformers, the circuit breaker which is to be tripped by the protective relay when it operates, and the signal level required to operate the relay is selected when the relay is applied to the power system. The function of protective relaying is to immediately remove any component of a power system when it suffers a fault that might result in damage to property or unsafe conditions. In addition, protective relays can provide information on the locations and types of failures that occur. This information not only helps with equipment repair, but also provides the means for analyzing the effectiveness of the protection scheme. We should note that protective relays are not always part of a protection scheme. Fusing, reclosers, and sectionalizers are employed in some cases to keep costs down. Circuit breakers are located between each power system component, which makes it possible to isolate and disconnect the faulty component. If a breaker isn't installed between two adjacent components, both components will need to be disconnected for a failure in either one. One of the protection engineer's most powerful tools is the concept of zones of protection. The boundary of a protective zone represents the region that a particular protective element covers. It is necessary for these zones to overlap to ensure proper protection. If two zones did not overlap and a fault occurred at the boundaries of these zones, it is possible that no relays would be tripped. For failures within the overlap area, more breakers will be tripped than needed to disconnect the faulty element. However, the overlap areas are relatively small, and the probability of failure in this region is very low. Therefore, the tripping of too many breakers for a fault in the overlap area will be infrequent. The preferred practice is that adjacent protective zones overlap around the circuit breaker, so that for failures anywhere other than in the region of the overlap, the minimum number of circuit breakers will be tripped. If the zones of protection are set up such that overlap occurs on only one side of the breaker, the relaying equipment of the zone that overlaps the breaker must also be able to trip the breakers of the neighboring zone in order to completely disconnect faults in certain areas. This can be illustrated in the following example. For a fault located as shown, the circuit breakers of Zone B will trip, but because the fault is outside Zone A, the relaying equipment of Zone B will need to send a trip signal to the breaker in Zone A. A potential drawback of this is that the breaker in Zone A will be tripped unnecessarily for faults occurring in Zone B to the right of breaker C. There are 4 characteristics required by any protective relaying system to ensure that it performs its function properly. These are sensitivity, selectivity, speed, and reliability. The relay must be sensitive enough to operate under the minimum conditions expected. In any power system at various times of the day and during various seasons of the year, the load varies over a wide range. To meet these changing requirements, various combinations of generating sources are switched in and out of the system to provide efficient operation. The relay must be sensitive enough to detect a fault on the system when the minimum amount of power is being generated on the system. The selectivity of a protective relay is its ability to trip the minimum number of circuit breakers to clear a fault. The relay must be able to select faults in its own zone of protection and ignore faults in adjoining zones. Some relaying schemes are inherently selective. That is, they are unaffected by faults outside of their own zone. Other types of relaying, which operate with a time delay for faults outside of the protected zone, are said to be relatively selective. The speed at which a damaged power system component is isolated from the rest of the system has a direct bearing on the damage done by a short circuit and, consequently, the cost and the delay in making repairs. Therefore, speed is essential for most relaying applications. The speed of operation also has a direct effect on the general stability of the power system. During a short circuit fault, the rest of the power system can transmit less power because the various sources of generation tend to go out of synchronism. The shorter amount of time a fault is allowed to persist, the smaller its effect is on synchronism or stability of the system. For a protection scheme to perform properly, it must be reliable. With respect to protective relaying, reliability is made up of two components: dependability and security. It is important to understand the difference between dependability and security. Dependability is the amount of certainty that a relay will clear the faults that it is programmed to clear, whereas security is the amount of certainty that the same relay will not react to faults that fall outside of its zone of protection, or react incorrectly for a fault within its zone of protection. Generally, when the dependability of a relay is increased, the security decreases, and vice versa. For example, let's increase the sensitivity of one of the relays in our example protection scheme to be as dependable as possible. Now, when a fault occurs within this relay's protective zone, our relay is sure to identify and clear the fault. However, when a fault occurs outside of this relay's established zone of protection, it attempts to clear the fault. This is because the relay has been made so sensitive that it identifies and reacts to faults even though they fall outside of its zone of protection. In general, the most common faults that occur on a power system are short circuits. We will now consider relays that are dedicated to protection against short circuits. There are two groups. The first group are called primary relays and are the first line of defense, while the second are called backup relays and function only when the primary relaying fails. Backup relaying can be classified as either local or remote. Faster reacting backup relaying can be achieved by using local backup relaying systems. This means that the relay providing the backup is located on the same component that is being protected by the primary relay. Local backup protection is often used to protect against failure of both the primary relaying system and the associated circuit breaker. The only potential drawback is that local backup relaying often uses the same CTs, VTs, circuit breakers, etc., which can fail, likely resulting in both the primary and local backup relay to also fail. Duplicate systems. On high-voltage systems, it is a common practice to duplicate the protection systems to ensure proper operation if a failure occurs. In some cases, only the relays are duplicated, while in other cases, the entire protection system is duplicated. This is the preferred choice when economically justifiable. Let's take a look at several backup strategies being used within one power system transmission line. Here, we see that relays R1 through R6 are the primary relaying. The D group of relays is the duplicate system, and the L group of relays is the local backup relaying. When a fault occurs at location F, relays R1 and R2 are the primary relays that are programmed to identify and clear the fault. The fault at location F is within R2's zone of protection. Let's assume that when the fault occurs, R2 fails to operate. The duplicate relay, D2, should have operated at the same time. However, let's assume that relay D2 of the duplicate system has also failed. The local backup relay L2 should now operate a short time after the primary and duplicate relays due to its coordination with them. If all three fail, the backup function of relays R3 through R6 is to provide remote backup to R2, D2, and L2. Relays R3 to R6 will initiate breaker failure logic to trip all the adjacent breakers, which are feeding this fault if the primary or backup protection fails. Let's look at an example of a breaker failure protective element. In this example, the protective relays operate correctly, but the associated circuit breaker fails to clear the fault because of some malfunction within the breaker or its control circuits. The fault will now remain on the system until some other means is used to clear it. In our example, the primary or backup relays start a timer once a fault has been detected. The timer will then time out and send a trip signal to all breakers that can feed the failed breaker with power. Until the early 80s, almost all protective relays in use were based on an electromechanical principle of operation. Their designs were limited in configuration, and most supported only one protective element, resulting in a requirement for many expensive electromechanical relays for a protective solution. This, coupled with the expense of periodic calibration, translated into high initial cost for an electromechanical relaying solution, in addition to high maintenance costs associated with the mandatory periodic calibration of each electromechanical relay within the system. In electromechanical relays, a moving part like a disc or a plunger is placed in a magnetic field produced by the input signals known as actuating signals or measured quantity. The disc or the plunger moves and touches a contact when the intensity of the magnetic field exceeds a preset limit. Electromechanical relays fall into one of four styles or categories depending on the type of moving part. These are the plunger, the hinged armature, the induction disc, and the induction cup. The plunger and hinged armature operate under the principle of magnetic attraction. The armature is attracted into a coil or to the pole face of an electromagnet. This principle works with either alternating or direct current measured quantities. The induction disc and induction cup work under the principle of magnetic induction. Torque is developed in a movable rotor in the same way that it is produced in an induction motor, which means that they can only be used with alternating current measured quantities. Now let's quickly review the theory of operation of each style of electromechanical relay. The plunger style of construction consists of a bar or cylinder armature, which is attracted axially into a solenoid coil. The armature carries the moving portion of the contact, which meets a fixed contact once the current magnitude of the measured quantity exceeded a preset amount. The hinged armature construction, which also includes the cantilever and beam type of construction, consists of a flat plate or bar type of armature, which pivots at a fixed point when attracted to the pole face of an electromagnet. The armature carries the moving portion of the contact, which meets a fixed contact when the armature is picked up. An advantage of the plunger and hinged armature style of construction is that they have no inherent time delay, hence they are used for functions which require instantaneous operation. As the hinged armature relays operate, the length of the magnetic air gap changes, resulting in a slightly greater force required to just pick up the armature than the amount of force that is required to release the armature. This translates into a difference in the amount of measured quantities for pickup and dropout, which is a slight impairment for this style of relay. This shortcoming also applies to the plunger style of construction, but to a lesser extent. The induction disc element consists of a metallic disc of copper or aluminum, which rotates between the pole faces of an electromagnet. There are two styles of induction disc, the shaded pole style and the watt-metric style, each having its own principles of operation. Shaded pole. A portion of the electromagnet pole face is short-circuited by a copper ring or coil, which causes the flux in the shaded section to lag the flux in the unshaded section. Once the measured quantity exceeds a preset level, the induced torque on the disc will cause it to rotate, resulting in contact closure. A spring on the disc allows the contacts to open once the measured quantity falls below a preset level. Watt-metric. This style uses one set of coils above the disc and another set of coils below the disc. In either case, the moving contact is carried on the rotating shaft of the disc element. The induction disc style of relay is always used as a time delay element because of the inertia of the moving disc. The time delay feature is added by means of a permanent magnet. The disc rotating between the poles of this magnet causes an induction drag. The induction cup element consists of a metallic cylinder with one end closed like a cup. The cup rotates in an annular air gap between the pole faces of electromagnets and a central core. The induction cup unit uses 4 or 8 poles spaced symmetrically about the circumference of the cup. Due to the low inertia of the rotating parts of the relay, this style is capable of high-speed operation, hence it is used for functions requiring instantaneous operation. The multiplicity of poles also permits measurement of more than one electrical quantity. In the 1970s, many relay manufacturers introduced electronic relays, which simply emulated their electromechanical predecessors, and in many cases, the design still required costly periodic calibration. In the early 80s, the microprocessor-based relay, or digital relay, was introduced. Standard features such as multiple element support, low maintenance, built-in high-speed communication, waveform, event log, improved element performance, and built-in programmable logic controller functionality has enabled the digital relay to revolutionize the protection industry. Let's take a closer look at the operation of a modern microprocessor-based relay. Through the use of current and voltage transformers, the relay receives information about the power system. These measured quantities need to be converted into symmetrical components. Filtering removes high-frequency noise and DC offsets. Analog to digital converters then take this analog waveform and convert it into a digital quantity. The resulting digital quantity, which is a true replica of the power system quantity, is then input into the microprocessor's active protective elements within the relay. The protective element or elements within the relay initiates the appropriate action based on these quantities and the configuration settings within the relay. These elements may work independent or through the use of logic gates. The type and number of protective elements within a particular relay will depend upon the type of protection application the relay has been designed for. For example, a relay designed to protect a transformer will have some protective elements not found in a relay designed to protect a feeder, and vice versa.